First-year statics focuses on structures that are perfectly balanced in equilibrium, but mechanics of materials examines the internal physical response of the material when those external forces are applied. If a body cannot adapt to external loads, it is rigid. When pushed past its physical limits, it fractures abruptly with zero plastic deformation. Deformable bodies behave differently. Metals, for example, yield and stretch to physically absorb the applied load. We calculate this internal response for two primary reasons. We either need to determine the required geometric dimensions and materials to design a new mechanical part, or we must verify the safety of an existing structure under working loads. By understanding exactly how a specific material yields, engineers calculate structural limits and prevent failure before a component is manufactured. This chart maps the stress-strain curve for four materials.
The pure iron plot stretches horizontally, showing high ductility before breaking. The quenched alloy steel at the top absorbs massive stress, but allows almost zero elongation. A part fails when it breaches one of two conditions. The first is strength. If the actual internal stress exceeds the material's maximum allowable stress, it breaks. The second condition is rigidity. A part is considered to have failed if its actual deformation exceeds the allowable limit, even if the material remains in one piece. Structural integrity requires a precise balance. The material must possess the strength to resist fracturing and the rigidity to maintain its required geometric shape. To calculate stress, we must first map the internal loads that are generated inside the structure to resist the external forces. These internal loads manifest in two ways. Forces causing a change in physical size generate normal stress. Forces causing a change in physical shape generate shear stress. This vertically oriented column illustrates internal force distribution. Notice the external loads, 5 kilonewtons at the top, then 6 and 4.5 kilonewtons at the brackets. Slicing the structure, seen right, exposes the central normal axis, revealing the specific internal force resisting loads at that cross-section. Stress is highly localized. You cannot determine the stress at a specific point without first conceptually slicing the structure to evaluate the internal force distribution at that precise location. Solving any stress analysis problem requires a strict three-step methodology. Step 1 is always isolating the geometry by drawing a free body diagram. Step 2 is calculating the reaction components at the supports using basic equilibrium equations, where the sum of forces and moments must equal 0. Step 3 is drawing the internal loading diagrams, starting with the normal force diagram to map axial loads pulling or pushing on the structure. We then map internal forces running parallel to the cross-section using a shear force diagram, and map bending forces using a bending moment diagram. These diagrams adhere to a strict sign convention. Positive values are plotted above the central axis line, and negative values are plotted below. For circular components, like structural pins or rods, we calculate allowable limits using area equations, derived directly from the allowable tensile or shear stress. These internal loading diagrams provide the precise mathematical coordinates of where the part experiences peak load and is most likely to fail. Standard statics equations have operational limits. When a structure has more constraints than necessary for equilibrium, it becomes statically indeterminate. Consider a metal rod fixed between two unmoving walls, with an external force pushing horizontally from its center. Because both walls react, our equilibrium equation is reaction A plus reaction B equals P. Two unknowns creates a mathematical dead end. To solve the system, we must apply the principle of superposition and introduce a compatibility condition based on the physical deformations. Substituting deformation formulas into this compatibility condition allows us to solve for the reaction force at the first wall, providing the missing data point to resolve the entire system. When purely force-based equations fail, engineers calculate the missing variables by relying on the physical boundaries and geometric constraints of the structure. Temperature changes cause dimensional shifts called thermal loads. Expansion depends on the material's thermal coefficient, the temperature delta, and its original length. This creates the gap problem. Imagine a rod fixed to a wall on one side, with a designated physical gap between its free end and a second rigid wall. Applying heat causes the rod to expand across the open space. In case 1, if thermal expansion is less than the gap, the rod expands freely. Reaction force and internal stress remain 0.
But if temperature continues rising, the rod slams into the second wall, generating a massive opposing reaction vector. In case 2, the expansion exceeds the gap. The system is governed by a strict equation. Total thermal deformation equals the physical gap plus the mechanical deformation caused by the wall pushing back. In this constrained scenario, physical strain is calculated relative to the gap distance, as the rigid wall establishes a terminal point for all linear growth. Successfully analyzing mechanical or thermal loads depends on the rigorous application of physical boundaries, compatibility constraints, and internal force mapping.